Before solving this problem, let's do this little puzzle. So I want to figure out what this angles measurement's up here. I have a right triangle. It's got 30 degrees at the bottom right. And then you can see there's a dotted little triangle connected to the blue triangle. And it's got a perpendicular to the hypotenuse of the blue triangle. And I want to know what that little angle is up there in the corner. Take a moment and try to solve it on your own. And then start the video up again. All right, the answer is 30 degrees. How did I get 30 degrees? Well, if I look at it, the blue triangle is 90, 30, and I know that all the angles add up to 180 inside of a triangle. So this is actually a 30, 60, 90 triangle. So that little angle up there is 60 degrees inside the blue triangle. Now I know the angle inside the blue triangle at the top plus the little angle I'm after, they add up to 90 degrees. See the little 90-degree box in the top left-hand corner? So I know that 90 degrees equals 60 plus theta. That means theta, the angle I'm looking for, is 30 degrees. It's no coincidence that it's the same angle as down there in the bottom corner. So remember this little trick is going to help us when we're solving the problem. Here's the problem. What is the speed of the ball at the bottom of the incline? It gives me a coefficient of friction of 0.35. It starts from rest, moves 1.25 meters, and that's a 34-degree angle. So if I look at it, my kinematics givens, I know the initial velocity, I know x is 1.25. The final velocity is what I'm after, and I wish I had the acceleration, but I don't. But the acceleration I can find with a net force, with a free body diagram and a net force. So that can be part of my strategy. So here's what I'm going to do to solve this problem. It's a lot of work. Number one, I'm going to use kinematics to find the final velocity. So I'm thinking about this like from the last step. What's the speed of the ball? I'm going to use kinematics to find that. And then I'm going to use when I look at it, I see I don't have the acceleration. So I'm going to use a free body diagram to find the acceleration. So now I know I got to create a free body diagram, and then I got to examine all the forces to do that. So I'm going to do this in reverse order on my paper. That's what I'm going to do, starting from 4, working down to number 1. All right, step 1, examine all the forces. So in other words, we're creating our free body diagram. Here's my dot. That's the ball. And I'm going to put a dotted line to indicate the incline and what's perpendicular to the incline. Now, if I was doing my paper, I'd probably do this just with a colored pencil. Maybe have one around when I'm doing this whole unit, maybe a red pencil or a blue pencil or both. And then I do all my work in a regular pencil. You can see I've got the little corner down there. It's 34 degrees. That's going to be handy. All right, examine the forces. First question, is the ball on a planet? The answer is yes. So therefore I have weight. So I'm going to draw a vector going down. Hey, that looks kind of like a triangle down there. Ooh, that little shortcut we did, the puzzle in the beginning, is going to come in handy. All right, next question. Is there a contact surface? Yeah, it's rolling down an incline. So if there's a contact surface, that means I have a normal force. So there's my Greek letter eta for normal force. And that line that I drew is perpendicular to the surface, or perpendicular to the incline. Remember, that's what normal means. Normal means perpendicular or 90 degrees. So it's all set up. Is there surface friction? Well, let's see. It says the coefficient of friction is 0.35. So yeah, if there's a coefficient of friction, there's surface friction. So that does exist. So I got friction going on here as well. And friction, remember, that's parallel to the surface, opposite the direction of motion. So it's going to be along the incline and going up because the ball's rolling down. Is there a rope? No. Are there any other forces? Nope. No other forces. Oh, velocity. Is there a changing velocity? Yes. It starts at rest and reaches some final speed. So there's a net force. And the net force is the only force we don't draw on the diagram because it doesn't affect the ball. It's what happens when you add up all the other forces, you get the net force, which looks like this. We think the ball is going to accelerate down the incline, so that's where the net force would go. All right, so there's our first free body diagram. But remember, College Board rules, they say you got to draw 2 free body diagrams. So the second free body diagram's got to have components on it. All right, so now I redraw everything. So I draw it all over again. On my paper, I'll draw 2. So this is going to be my second free body diagram with components. And I'm going to put components, well, let's see. When I'm looking at this, I need to make some axes, a kind of reference point. And I'm going to make the axes parallel to the net acceleration and perpendicular to the net acceleration. It's going to make my life so much easier mathematically to do that. In other words, parallel to the incline and perpendicular to the incline. So if I didn't have MA net there, I would still go parallel to the incline and perpendicular to the incline. Again, it'll make the math easier most of the calculations we do. All right, that's great. So normal force, I don't need to break that up into components because it's already perpendicular to the incline. Friction, that's parallel to the incline. I don't need to break that up into components. Mg, oh, wow, that's at an angle to the incline. That's definitely not parallel or perpendicular. So that's going to become the one I got to break up into components. So Mg, that vector, is going to be the hypotenuse of a triangle. One side of the triangle is going to be here. It's going to be perpendicular to the incline. The other side of the triangle is going to be tip to tail to this red vector and end up at the bottom of mg as well. And the key thing about this is mg sine 34 is parallel to the incline and mg cosine 34 is perpendicular. A lot of times people will make a mistake and they'll make the mg cosine, they'll draw it parallel to the ground, not the incline. And that's not right. It doesn't look right. It'll just mess everything up. So it's got to be parallel to the incline. Okay, now I'm going to sum up the forces according to my x and y coordinate axis that I drew on the page. Sum of the forces in the x direction, so that's going to be everything, let's say it's going to be equal to ma net going down the incline. So I'm going to make down the incline positive to make the math easier. I'll just always make ma net positive. And mg sine 34 goes the same direction as ma net, so it has the same sign. Friction goes the opposite direction of ma net, so it's the opposite sign. And I'm done. Notice it doesn't include the normal force because it's not parallel to the incline. It doesn't include mg cosine 34 because it's not parallel to the incline in the x direction. Now, switch gears. Sum of the forces in the y direction. In the y direction, there is no net force because perpendicular to the incline, the ball is not shooting off and accelerating in that direction. So there's no net force in that direction. So I'm just going to make it everything up minus everything down. So normal force minus mg cosine 34. Easy peasy. Now here's something interesting. A lot of times when I have an incline and I have friction, I have this cool substitution that we'll do almost all the time. And that's between friction and normal force. See, friction is equal to mu times eta. That's the normal force. So a lot of times at some point I'm going to replace friction with mu times eta. And I'll use that to solve it. So knowing that's typical, what I'm going to do is I'm going to take some of the forces in the y direction and just set eta equal to mg cosine 34. So I'm just rearranging that part of the equation. Now remember, friction's fun. F is equal to mu times eta. So now comes all these substitutions. I'll start with the long equation up here. And what I'm going to do is I'm going to replace friction with its equation, mu times eta. So I'll rewrite it. There it is. ma net equals mg sine 34 minus mu times eta. So now when I'm looking at this, I see the eta, and I'm like, oh, I know eta is mg sine 34. So we're going to do it again. We're going to do one more substitution in here for eta. So now it looks really long. Oh, wait, it's not that bad because there's ma net, mg sine 34, and mu mg cosine. Hey, there's an m in every expression that's there. Because there's an m in every expression, what I can do is and I know that mass isn't going to be 0, so I can divide out the mass. So I'll divide everything by m. That leaves a is equal to g sine 34 minus mu g cosine 34. And remember, sine 34 looks a little intimidating, but it's just a number stored in a table in a calculator. So now I'll put my numbers in, and there's no negative sign on any of the kinematics variables that we had, like negative 9 point, anything like that. That doesn't happen anymore because we're using a free body logic to figure out what the directions are. And now my net acceleration comes out to be 2.64 meters per second. All right, still not quite the answer. I'm looking for the final velocity, but I'm on the way because now I have one more kinematics given that I can use. So because I'm doing this the way I am, I'm going to get rid of some of this stuff to make some room. There we go. So let's go back to kinematics. And there are my givens. There's my acceleration with all the decimals. I don't want to leave any of them off. Don't round now. You're almost there. Initial velocity was 0. The distance is 1.25 meters. And I want to figure out what the velocity is at the bottom. Cool. I've got 3 of my kinematics variables. I can find the 4th, which is velocity. I can use v squared equals v naught squared plus 2ax, putting in all my units, all my numbers and units, and all those decimal places. I get the final velocity at the bottom to be 2.57 meters per second. Crazy, man. And it's a lot of work. Here's what your paper would actually look like. So you can see the top left, I've got the free body diagram. Next to it, I've got another one with components. And those diagrams are big. They're not small. They're like 2 inches tall apiece. 5 centimeters, 6 centimeters. They're big diagrams because you're adding all kinds of details that need to be read. So don't think small, think big. Then I summed up the forces and it reads just in a column. I know I have a lot of wasted space off to the right, but this reads so clearly just from top to bottom as we would read anything. So keep it in a column. It's okay that you're not using up all the space. It makes what you're doing very clear and easy to read when you do this.